right, now. And some people are. All right, so quiz. We've got, now again, so I've got these graphs drawn, but that was just to visualize a global max, a local max, increasing inflection points, all that stuff. We're working with equations. Even when you have the calculator in your hand, we have to be showing our work. We have to write down, or at least write down what our calculator is doing. So if you're solving, doing the derivative setting equals 0, or doing the second derivative and setting equals 0, you've got to write that on your paper. You've got to write that equation on your paper. And don't forget the equals 0. Some of you did that on this quiz, right? You just wrote down the derivative and then these numbers appeared out of nowhere. Where'd those numbers come from? You're solving an equation. So write the equation equals 0. Okay, that's what you're doing. So even if you're letting the calculator then solve it for you. Okay? Now, local max min, any increasing, decreasing, anything from the chart, we're doing number lines. We're setting it equal to 0, putting those numbers on the number line, picking numbers in between, plugging those into F prime and F double prime to get our chart information, which tells us everything we need. Local max min's on there, inflection points are on there, it's all there. Okay? Global max min is different. We've got these two candidates where the derivative is 0, here, here, and here, or at the endpoints. Those are the only places that the high and low spots could be. Those blue dots are the only possible places you could have the highest and the lowest spot. And that's what a global max min is. So we call those our candidates. So where the derivative is 0, which is your stationary points, and your endpoints, and we're going to make a list of candidates, and we're going to plug those into the original function. Why? Why the original?
Y values.
We need the y value, right? Because we want to know what the highest y value is, and we want to know what the lowest y value is. So the whole point of a list of candidates is to compare. Compare their y values. See which one's the biggest, see which one's the littlest. But we narrow it down by our candidates. Those are the only places we have to check for high and low y values, is where the derivative is 0 and at the endpoints. So if it's a calculator problem, and to be honest, tomorrow, global max min, I'm going to put on the calculator one, because we did that one without a calculator the other day, and we were getting these weird pi values, and we had to estimate them in our head. And I don't want that to get in the way right now. So if it's a global max min, you have to plug it back into the original function. It'll be on the calculator one, so you can go there. But you still have to have this on your paper, that these are what you're checking. But then you can plug in a 1, plug in a 2, whatever, into your calculator to get those values. Okay? All right. So let's do that right now. So on the homework, give me one of the problems. Whoops. Give me one of the problems that was a local max min or a global max min or something like that. 41? F of x. Now, here's the other thing. Some of you on that quiz, a couple quizzes ago, the problem was h of x, and you kept writing f in all your work. Write down what the function is. If it's g, use g. If it's h, use h. Okay? Is this one f?
G.
Is it? 40. Was it 41? Is that the one that had the square root of 3 in it?
Yeah.
Okay, that's the one I want to do. G? Is it g?
Yeah.
Okay, good. G of x equals 2 sine of x
Minus square root of 3x.
Now, I don't know if any of you noticed, some of you did and some of you didn't, the square root stops at the 3. The square root is not over the x. If it was over the x, we wouldn't even be messing with that. That would make that way too hard. These are no calculator one. It's going to involve trig. I told you that multiple times now. And it's going to be nice values. Root 3 over 2, 1/2. Those, root 2 over 2. Those nice trig values. Okay? So, what do we do here? We do the derivative, right? Now, on 41, and again, I mentioned this the other day, but on 41, the directions said a bunch of stuff. So let's talk about that. 41, and we did 37 the other day, and okay? On 41, it says, draw the graph of f. I'm not going to have you do that. Don't worry about that. It said, but if you get done, if you find the local max and mins, and you find the inflection points, and you find all these points, you certainly could plug them into the original, get their y values, you'd have a whole bunch of points, you could plot them, and you could draw the graph pretty quickly. Matter of fact, in the old days, for the graphing calculators, this is how we would draw these functions a lot of times. We would find all these important points, and we would plot them, and then that would give us a picture of the f graph. Okay, so don't worry about that. We're not going to do that. Okay, and it says show both coordinates. Again, that just once you find them, plug them into the original. Right now, the only time I'm going to ask you to plug back into the original is on a global max-min problem, where we're doing our list of candidates. Okay, so if it's a local max, we're just going to give the x value. Flexion points, just give the x value. Okay, all right. So let's focus on this one, on just the local max-min part of it, and just the inflection point part of it. Okay, let's just focus on that. All right, so we're going to do the derivative, and we get what? 2 cosine minus root 3. Because think of root 3 times x is just 7x or 6x or 5x, and the derivative of that is just 7 or 6 or 5, right? It's whatever number's in front of the x. So that's it. Okay, so now we're going to solve that. This would be a no calculator one right here. Okay, and then we're going to divide by 2. And we get cosine equals root 3 over 2. Now this was supposed to be from where to where?
0 to pi, 2 pi.
2 pi. 0 to 2 pi. So, cosine is root 3 over 2 in this quadrant. And what other quadrant? Fourth, right? Cosine is the x. Cosine is the x. So it'd be in the first and the fourth. Cosine is positive. So that is what? What's across from a half? Pi 6 and 11 pi 6. So pi 6 and 11 pi 6 are our two stationary points. And what do we do with that? We put them on a number line. So this is this picture here. Now again, we don't have this. What we have is our equation. We did the derivative equals 0. We're now going to do a number line, because then all the information I need will be there. So I'm going to label it f prime. I'm going to do pi 6. I'm going to do 11 pi 6. And now I'm going to find some numbers in between. Like 0. Like pi. Like 2 pi. And I'm going to do what with those?
Plug them in.
Plug them in. Now, Marcus and I were just having a conversation about the calculator. People get freaked out about the calculator. The only thing that you really have to make sure you can do on a calculator, if this was a calculator problem, is you have to make sure you can type in you got to make sure you can type that in right there. If this was a calculator problem, you would then want to solve that. Now, it would be some weird numbers here that we couldn't do in our head, right? That's why we would need to calculate. So at this point, you would need to be able to do that on your calculator. The thing with define and all that other stuff, you wouldn't have to do. Okay? You wouldn't have to do it all. As long as you understand that you can solve your f prime, your f double prime, and the vertical bar goes on the outside and it's between 0 and 2 pi, as long as you can do that, it's really all you need your calculator for. Now, at this point, we now need to plug these 0 pi and 2 pi into f prime, right? So I showed you on your calculator some ways to do that with the vertical bar and all that stuff, but you don't need that. You know, if that didn't make sense to you, don't do that. So we're going to plug 0 in here for x, right? So if you were using your calculator, just go 2 cosine 0 minus root 3, right? Just do that. It might take a little longer to type all this, but that's okay. And then we're going to plug a pi in, right? So then you would do 2 cosine pi minus root 3, right? And you just type that in your calculator, right? See what you get. Now this happens to be a no calculator one right now, so we have to be able to do that in our head, right? So we're going to put a 0 in. Cosine of 0 is 1, 2 minus, what's root 3? It's definitely less than 2, right? It's less than root 4. So 2 minus root 3 is going to be positive. Now we put pi in. Cosine of pi is negative 1. So that would be negative 2 minus root 3. That's negative. And then cosine of 2 pi is 1. So that would be positive again, 2 minus root 3. So now, everything you need about the chart is right there, right? If I ask, where is F increasing? No. From 0 to pi 6 and from 11 pi 6 to 2 pi. Where's it decreasing? Here. Where's their local max? Pi 6. When F prime changes from positive to negative, F changes from increasing to decreasing. Local min, right? 11 pi 6 and all that stuff. So everything in the chart about F prime is right there in that number. Okay, we solve for 0, find our stationary points, put it on. We pick numbers in between, and we plug those back into our G problem. Okay? So if this was a calculator problem, we would have solved here. That would have given us the pi 6 and the 11 pi 6. We'd have put that on a number line. We'd have picked numbers in between, and then we'd have just plugged those into our F prime. So does that make sense, Marcus, what I'm talking about there? So, yeah.
So when we're finding the global max or min, do we plug the numbers into the G of prime equation or into the G equation?
Okay.
Find out more than the stationary point.
Okay, so when we're doing global max min, what do we want? Global max min of G, what do we want? The biggest Y value, right, and the littlest Y value of G. So how would we get the Y value of G? Plug it into the G graph. In other words, I don't want you to memorize it, I want you to think about what you're trying to find, right? In this, we're plugging into the G prime. Why? Because we want to know if G prime is positive or if G prime is negative, right? So we plug into G prime to get that information, right? But if we're doing global max min, we want to know the highest Y value and the lowest Y value of G. So therefore, we have to plug into the G function to get those Y values, right? So if this was a global max min problem also, right? We could do that right now. Now, what do we plug into G if it's a global max min? Where the derivative is 0 or the endpoints, right? That's our candidates for a global max min. It's the only place the high and low spots can be. Yes?
So like in this problem, could you just assume that the global max is pi 6 because it's the only local max on the system. So
But see, that's where you forget about endpoints, and that's why I drew this picture right here. Here's the only local minimum in this situation. Is it the global minimum?
No.
Because what happens is the graph goes back down. The question is how far does it go back down? So that's a great question. So let's look at it. So what do I know from the number line? And see, now look at, nobody called me out on it. You guys should yell at me. Look what I did right here. You noticed it, didn't you? Should have said something. That was bad. I should have wrote G prime there. I should have wrote G prime. Now, I'm not saying if you do that, I'm not saying I'm going to count off on that. Okay? Right now. If it was in a spot where it kind of mattered, right, where it's really important, that would be. Now, what do we know just from this number line? Tell me what we know about G. I'm not encouraging you to draw the G graph because I think it's unnecessary. But just for understanding, what do we know the G graph is going to do? It's going to go up,
then down,
down,
and then up.
then up. What we don't know is when it first goes up, how far does it go up? Did it go up from here and go up a lot, or did it just go up a little bit? The other thing, when it goes up at the end. So, like, Matt, your question was, do we know that'll be the max? Well, at the end, it goes back up, right? So did it go up and stop right there? Or did it go up and go up to there? We don't know unless we plug into the G equation, right? Unless we plug the endpoints and the stationary points into the G equation, we don't know where those Y values are. And that's why we do our list of candidates. So over here, now again, the red is just for a global now. The red part would be just for the part of this problem that said global. We would do G of 0. We would do G of 2 pi. We would do G of pi 6. And we would do G of 11 pi 6. Now I told you I'm not going to make you do this on the no calculator part, right? Okay? So we would do it on the I would only have this on the calculator part. Now you would take 0, 2 pi, this, and we plug that into this function. Now, last week I was showing you how you could have defined this as your g function, so now you can just type in g of 0, g of 2 pi, but you don't have to, right? You don't have to. Right now, you want to plug a 0 into this, just type in 2 times sine 0 minus square root of 3 times 0, right? Just like you would if you were using an old TI-30, right? That's how you would plug something in for the x, right? Just do it that way. If that other stuff I was showing you in the calculator doesn't make sense. Okay? So then you would find out where your highest and lowest points are from the y-limit. Okay? All right. And then the inflection points would be the same thing, except we would do what now? We would do the second derivative, right? So we would do the second derivative. So derivative of cosine is, so that'd be negative 2 sine. Derivative of that, that's just 0. It's a number. So that's just 0. So we'd set that equal to 0, maybe divide by negative 2. So it'd still be 0. So where is sine 0? At 0, pi, 2 pi. Now, to be honest, we can ignore those because they're at the endpoints. Inflection points. Well, why would I ignore the endpoints? And I'm not going to give you a problem where that happens. And if you don't ignore them, if you put them on there, I won't count that off against you. But what do we have to check to see if something's an inflection point? Same thing goes for local max min. We got to tell if it switches. But at our endpoint, we have nothing on the other side, right, to tell. So local max, local min, inflection points, if they happen at endpoint, we usually just ignore them. Okay? So we would just worry about pi. So we would make a number line just like we did here, and we would pick some numbers on either side. Pi halves, 3 pi halves. Now, I would make sure to plug it into this version of g double prime before I took out that negative, because that's going to affect my answers here. So I put in pi halves. What's sine of pi halves? Times negative 2, negative. 3 pi halves, sine of 3 pi halves is negative 1 times negative 2. So what does that tell us about g?
It's switching from concave down.
Switching from concave down to concave up. So we do have an inflection point at pi, and that's what you would say, because that shows you g double prime switches negative to positive. G is switching concave down to concave up. So all the chart stuff is there. Gives you all the chart stuff in there, and then global max min is just that list of candidates. Okay, that's probably half the quiz right there, those points. You do a couple problems like that with all the different parts of it, that's a lot of points. Okay? And again, there's the calculator part of that as well. So let's spend some time on is there anything else about the calculator piece of it? Just expect when you do the calculator, you're just going to get, instead of nice numbers like pi 6, you might get some decimals. Just make sure your final answer for all those, you go 3 decimal places at least.
So what were you saying you're going to do only
The global max min, because that's the one we got to plug in.
So we're going to have chart stuff with us.
And you might have chart stuff in both, the calculator and the no calculator. Chart stuff for sure, like there. The global max min, because we do a lot of plugging back into the function, and we have to plug in on the number line too, so there's a little bit of that. But you don't have, all there you have to know if it's positive or negative. You don't have to know these exact values, which you do on the global.
Can you do 45 just to go over the
Absolutely.
calculator?
Absolutely. So give me the equation on 45.
F of x equals cosine x plus 1/2 cosine 2x.
Right. Okay? So this, what did it ask? What did the question ask about?
Determine where f has local maxima and minima over the interval 1 to 5.
Okay?
0, 5.
And then it talked about inflection points? So that'd be the second derivative, right? Or again, imagine it was global max min, but because they all start the same, right? They all start by doing what? They all start, all these problems, global max min, local max min chart, they all start by doing what? Doing the derivative, set it equal to 0. They all start that way, because in global max min, you got to find your stationary points, because that's something you have to plug into the original. You have to do the derivative, set equals 0. And then, of course, the endpoints, which they just give you here, it's what, 0 and 5? Here, the endpoints are 0 and 5. So, and we want to do a number line for the local max min kind of stuff, so we're going to do the derivative, set it equal to 0. So they all start the same way. So, we need the derivative. Now, I showed you the other day, or I've showed you multiple days, how to do the derivative on your calculator, right? But you don't have to. You're supposed to know the derivative rules right now, right? There'll be a few problems on there on the derivative rules. So what's a derivative cosine? Negative sine.
Minus.
So derivative cosine's negative, so that's going to turn to a minus.
Minus sinus.
What happens to the half? It just hangs out?
Yeah.
But we're going to kick out a 2. So that'll cancel the half. So it'll end up just being sine 2x. Now, if you're not confident in doing that and want to check it, then by all means, Liz, you want to do it? Okay. No, it's okay. This we probably want some. Blair?
Blair can definitely.
Everybody's got confidence in you. We're not going to do much. We're not going to do much on it. Just, oh, there we see you graphed it. Now, that's fine, but remember, all of the points you get in the problem is all this work. So having the graph, so you can see the local max and min might feel comforting to you to be able to see them or whatever, and that's fine, but you've got to have all this supporting stuff. Okay, so we want to do the derivative set equal to 0. So let's do a solve on that. Oops. Now on the graph screen, is that the original function? That was the original function, right? That was the original. So we want the derivative. So go ahead and, does everyone see the derivative one more time? It's next to the 9. If you hit, let's have it do the derivative, Blair, one time here. Hit escape. There you go. Okay. So next to the 9, we grab that derivative piece, put an x down there, whatever the input variable is. And then we got cosine x. Oops, got a right arrow, get out of there. Plus 1/2, or you can do 0.5 is fine. Cosine 2x, because it's calculator one, we're going to use decimals probably anyway. I prefer to have decimals. And so now we're just doing the derivative of that. Okay, just hit enter. Okay, there it is. But you don't have to have the calculator do that, right? Okay, but that's how you do the derivative if you want. Okay, so we're going to set that equal to 0. So let's do a solve. Okay. Now those dots you're seeing in there, that's a 2 dot because we're doing decimals, so it's treating that like a decimal. That's the only thing. So now she's just retyping it, which is fine. You can go up and grab it, but it doesn't matter if you haven't done that, not comfortable with it, that's fine. Minus sine x. So this is the one thing you've got to make sure you can do. You've got to be able to solve something. So the equal 0 has to be inside. Okay, we want to arrow back to the left one place. We got to do equals, so we got our derivative. We're going to go equals 0. We're going to go comma x to tell it to solve for x. And then we go outside of the solve and we do the 0 less than or equal to, yeah, we need the vertical bar. I'm sorry, I didn't say that. Yeah, vertical bar. And that's the equal sign. So control and the equal sign, you can see the little vertical bar there, which means with. So we're telling it right now we're going to solve with this parameter, 0 less than or equal to x. What is it, 5?
Yeah.
Less than or equal to x, less than or equal to 5. And hit enter. Okay? So 0 2.09, you can arrow up and scroll to the right if you think you're missing some. Maybe there's some we can't see. Yep, there was one we can't see. So that's x equals 0. What was it? 2.09.
2 pi thirds. I got 2 pi thirds in mine.
Yours came out 2 pi thirds.
Yeah, I used hat.
She used the decimal there, but she didn't on this last one we typed in. That's okay. That's what it is, but I don't care. I don't care. That's fine. If it gives you 2 pi thirds, that's fine. Next one was 3.141, which of course is pi, right? And then 4.18 something. 4.188. Right? But that's 2 pi thirds and pi and what? 4 pi thirds?
Yeah.
4 pi thirds, which is fine. If that's what it gives you, write those down. If it gives you decimals, write the decimals. Yes.
Would that be all we need to write down on your paper?
Right. Because the whole point is it's okay to use your calculator to solve an equation, but you've got to have the equation on your paper that you're solving, right? But yeah, you won't have anything else other than that. You let the calculator solve it. Now what do we do with those numbers? We put them on a number line. Okay? So, 0, 2.094, 3.141, and 4.188. Now remember, we're only going 0 to 5, so I'm not going to put anything over here. Right? So I got a 1, I got 3, I got 4, and I got 5 would be in between them. So now I want to plug those back into the red thing. So we're not going to go through that with all of them, but let's just do one, Blair. So we're going to plug a 1 into that. So she's going to, I like it. So just do that. So we're going to go, so you got negative sign, whoops, it'd be, here's your derivative right here. So we're going to plug a 1 in for x. So 2 times 1 would be 2, and then minus sign of 1. If you use pi thirds, maybe you pick different numbers, right? You might have picked pi numbers, that's fine. Hit enter. Oh, and it gives you that, so you say, oh, whoops, I'll just hit control enter, and it gives me that. And what do I care about that?
It's negative.
All I care there is it's negative, because I plug that into, I should label this as f prime. So we got negative. Now, doesn't it go positive, negative, positive? I think this one does. I don't think there's any flags left. I think it goes, it alternates. So she could go back in now and plug a 3 in, and she could plug a 4 in, she could plug a 5 in, and those are the numbers we would get. Okay? If you want to do that vertical bar thing I showed you with x equals, and there's all kinds of ways you can do it. You want to graph the f prime and trace. I mean, just think about what you're doing. You're just trying to find f prime values
That's just a check.
at 1, 3, 4, 5.
That's
Well,
just that, you just do that to make sure that it's not a flat spot, right?
right, we do that. Well, we not only make sure it's not a flat spot, but to tell where our local max and mins are. Right? There's a local min. There's a local min. There's a local max. Right? So yeah, so this is key. Right? This is key. It tells us everything we need.
So you just ignore 0?
Well, because yeah, we're only going from 0 to 5. Yeah, so that's our starting point. So I would not put anything. Now, if you did and put that down, I will ignore it. I won't count it off if you went ahead and plugged something over here and called this a local max. Let's say 0. That's fine. I'd say good for you, but you didn't have to do that. Okay. All right. So there you go. Okay. So the next part was inflection points. Now, just for time, we're not going to go through it, but you do all that again, right? You need f double prime. So you're going to do the derivative of the red thing. You're going to have that. You're going to set equal to 0. You're going to get some values, right? You're going to do a number line. You're going to put those on there. You're going to pick numbers in between. You're going to plug those back into f double prime, and you're going to see what's happening. And if it was a global max min, we would make a list of candidates. What are our candidates again? What is it for a global max min we plug back into the original? Where the derivative is 0 and the endpoints, right? We just take our stationary points, which we'd have 4 of them, and our endpoints, which actually our stationary point was one of the endpoints. So we'd have these 4 plus 5. We would take those, and we would plug them back into the original. And we would write down those y values, and we would have our list of them, and whichever one was the biggest y value, that's our global max. and whichever one was our smallest Y value, that's our global mean. That's it. That's it. Okay? So that, probably 75%, 70% of the quiz is this, and then just some derivative rules. Like, for example, if I just give you this function and want you to, and you just have to write that derivative. That'd be on the note calculator probably. Okay? So that would be all, just these derivative rules. Remember, if you got a number on the inside, we kick it out like the one we just saw. Remember, when you have e to the x or 2 to the x or 3 to the x, those aren't power rules. We don't bring the x down. That's only when you have x raised to a number.
Will we have to know the cotangent and tangent?
You know what? I wouldn't even spend time on those right now. We haven't hardly done any problems with that. I would stick with these simple trig ones. Right, yeah, we're definitely going to get into them, but the log ones, but I wouldn't worry about this last page of them. Okay? All right, so that's probably 70% of the quiz. All right, now, so let's talk about the differential equation. The vast majority of the differential equation points are going to come from this T-chart thing right here. Okay? So let's pick one out or several.
Yeah. All of them. 24.
Yeah, 24.
I don't know why.
Okay, let's look at 24. And I'll tell you, and I'll just show you some of the things I'm seeing people do here on their homework. So 24. This was in 2.5, I think. On page 129. It says y double prime equals 2y over x squared. Is that the one?
Yeah.
Oh, okay. I'm writing it backwards from what it is in the problem, right?
Yeah.
The problem says show that y equals x squared. So it doesn't matter. It doesn't matter what order I write it. X squared minus x to the negative 1. So it says show that this is a solution of this. And this isn't equals.
It's minus. It's a minus.
It's a minus and then an equals. Okay, so minus this equals 0. Now here's what I'm saying when people are coming in and asking questions. I'm seeing people go, okay, this is where he did that T chart, that line. And so I see it coming in and you got a line here. Well, I mean, no, I'm not being funny. It's just, there's some confusion as to where to put this line, right?
Yes.
And where does it go? It goes under the equal sign of what?
The one you're trying
The differential equation, the DE, the one that's got the primes in, right? Because this is our proposed solution. That's like the x equals 4 that we're plugging into the differential equation. So this bar doesn't go between the two things. It goes under that equal sign right there. Okay? Because here's why I put that bar. To me, it's like a wall. I got the left side of the wall, I got the right side of the wall. I'm trying to show that the left and right sides are the same. That's what I'm trying to do. So that's why I put that there. You don't have to put it, but I think it's the best and cleanest way to show this. All right. So now we substitute into the left side of the wall, and we substitute to the right side of the wall. Now sometimes there's nothing to substitute, like on this one. The right side of the wall is what? Always 0. Now I wouldn't add that 2yx squared over the other side. I wouldn't get into it. The wall is impenetrable.
Gotcha.
No one gets past that wall. We are not adding that thing over there. Don't move stuff around. Great Wall of China. All right. So there we got that. So this side is 0. This side we'll substitute in. Well, what are we going to put for y double prime?
2x.
Well, we need to do the derivative over here. Twice. So that would be 2x plus
x 2.
right? Bring the negative 1 down, would make it positive, and drop the power to a negative 2. Then I got to do it again.
2 minus.
Bring that down.
2x.
Okay? So, I want to make sure that we're just clear on the substituting and that stuff. Now, if you get lost in the algebra on a problem, there's not a lot I can do at this point, right, with your algebra skills. I mean, we'll keep practicing and that kind of thing, but that's what happens on this one. The algebra gets a little bit messy, okay? Probably not going to be that much on the quiz, but, I mean, you got to be able to do some algebra, okay? And so there's y double prime. So we got 2 minus 2x to the negative 3. Minus. And then I got this. I'm just going to put some parentheses there just to make sure, because this is going to get kind of messy here. So I got 2 times y. Well, there's y right there. So that's going to be 2 parentheses x squared minus x to the negative 1 all over x squared. Now, if this is going to be a solution, if this thing up here in the blue is going to be my solution, then this side better end up equaling 0. Okay? So let's do it. So I got 2 minus 2x to the negative 3 minus, now I got to do some stuff with this. Well, let's distribute that. That'd be 2x squared minus 2x to the negative 1 all over x squared. Now I'm going to do some more work with those parentheses. And what can I do here? How about I split it into 2 fractions? Can I do that?
Yeah.
Get a single denominator and split it up. So 2x squared over x squared
2
is just
2.
2, right?
Yeah.
And 2x to the negative 1 over x squared, we can subtract the powers. Or think about just flipping the x down, and then I'd end up with x to the third on the bottom. But x to the third on the bottom is the same as?
What?
Now I can distribute the negative 2 minus 2x to the negative 3 minus 2 plus 2x to the negative 3. Cancel. Cancel.
Oh, it's out.
0. So that was pretty messy algebra there. Usually it's not that messy. But really, our calculus work was done when we got to this level. We had done our derivative properly. We had the vertical bar in the right place, and we just substituted the stuff in. Then it was just a matter of working it through and seeing what happened. Now, if the 2 sides wouldn't have been equal, then you'd say it's not a solution. Okay? Yeah.
Is there going to be a question like number 48 or 49 on the test?
Let's talk about that, because there is a piece of 48 where we have to do this verify thing, so let's talk about that, because 48 is definitely possible. Not quite to that level, no. Pieces of that for sure. Okay, so for example, let's talk about this Torricelli's law. They give you the differential equation y prime equals negative k square root of y, right?
Yes, sir.
And they tell you at some point in the proceedings there, they tell you that their proposed solution to this is y equals 1/4, and I know they put it over 4, right? But I've told you many times I think it's better to use fractions than the division. I think division is more confusing. And then this is c minus kt to the second, right? That's their proposed solution to that differential equation. So at one of the parts, you're supposed to show that that is, right?
Yeah.
Which part?
B.
B. Okay, let's do part B. So this is the part we want to make sure we can do. See, did I put the vertical bar in the right place?
Yes,
Under the equal sign of the differential equation. We want to show that this is truly the solution to that. Because the solution to a differential equation is the original function y. And of course, a differential equation is just an equation that has one or more derivatives in it. So, on this side, I'm going to plug in, for the y, I'm going to plug this. Right? And on this side, I need y prime. Where do I get y prime? By doing the derivative of this. So y prime would be, I would bring the 2 down in front, which makes 1/2. The inside never changes to the first. And what is our x in this problem? T. T is x, right? If there's ever a number multiplied on the inside times the x or the t, what do we do with it? Kick it out. Is there a number multiplied times a t on the inside?
Yes.
What? Negative k. So we're going to kick out a negative k. Now I can take that negative k and bring it around front with the 1/2, correct?
Yeah.
And so this would be negative 1/2 k times c minus kt over here, correct? Because we had to kick out that negative k. Now let's simplify this. I got the square root of this mess. Well, what's the square root of 1/4? When you're timesing, it's okay. Square root of x squared y squared would be xy. When you're timesing them, right? If it's plus, that's no good, but timesing, it's okay. So what's the square root of 1/4? 1/2. Now what's the square root of c minus kt squared? Are those two equal?
That was a lot easier.
That wasn't hard. See.
Okay. Well, you know, but when they wrote it, it's all in how you write it, correct? And I'm going to try to. I'll keep them pretty vanilla. But I mean that divided by 4. Well, speak, you know, divided by 4, that made it confusing. If you write it as a 1/4, it's easy, right? Because we have a rule. If you have a number sitting out in front, right, it just sits there. So if I got a division problem, I'd rather write it as a fraction, so it's a number sitting out front. It fits my rule. All right, so that's part B. Now, what was part A?
Faster when the tank is half.
Oh.
When it's full.
So this is a little bit like question 49, but let's talk about this a little bit. Because this is something else I want you to be able to do, a very small part of it, but this is not that difficult. Does the water, it has to do with the very first sentence. It says the depth of the water in the tank is proportional to the square root of the depth of the liquid, right? That sentence right there. I think we should be able to write that equation in red just from that sentence. Now that's what 49 was. 49, you did not have to do any work to it. All you had to do was write it out. Isn't that what it said? Didn't it just say write the DE that describes that situation? Was that 49?
Sure is.
Yeah, just write the DE, or it first said, is it reasonable? And then in part B, it said, express that as a differential equation. So let me read that again. The rate, the depth is changing, or something like that, right, in 48? When a valve is open, the depth drops at a rate proportional to, that's where the K is. Like if I just say y equals k times x, that's y is proportional to x. The k is the constant of proportionality. So the rate, so that tells you y prime, is proportional to, there's the k. Why'd they put a negative on it? Because it's dropping. Okay, but even if you left the k off, then wouldn't that just make k negative? Right? In this case, is k going to be positive or negative? Is k going to be positive or negative?
It's going to be.
No, let's think about it now. Why is the depth of the liquid? Think of the chart. Why is the depth of the liquid? What's y doing when you open the valve?
It's decreasing.
Y is decreasing. So therefore, y prime has to be negative. This would be a great quiz question, be worth a point or whatever, but think about it. Is k positive or negative? Well, let's think it through. Y is the depth of the liquid. We open the valve, y has to be decreasing. So therefore, y prime has to be negative. So my reasoning would be y prime has to be negative. What's the value of y? Positive or negative? Positive. What's the square root of positive? Positive. So this has to be positive, right? So this whole thing has to be negative so that this will be negative. So what's k got to be?
Positive.
K's got to be positive, and then you got that negative out in front. So k would have to be, in this scenario, k would have to be positive. And a lot of times I'll get people rationalize that. They'll say, well, k has to be negative because the water's dropping. No, what's negative because the water's dropping? y prime. Y prime's negative because y is decreasing. But when you factor in all those other pieces, in this case, k would be positive. My point is this. If you write that differential equation and don't put the negative on there, if I was writing it, I just would have written this y prime equals k square root of y. And then what would have changed? K would have ended up being negative instead of positive, right? If the negative sign was not on there, k would be negative because we know y prime has to be negative, okay? But that's just kind of the situation, just being able to write that. So back to writing it. It's proportional to the rate, meaning y prime is proportional to, that's where the k comes from, the square root of the depth. And they told you the depth was what? So the square root of what? So we'll get to 49 in a minute and we'll write that one. Okay, so in A, is it dropping or whatever? That's where you get that. Okay, what did C say?
So suppose that for a certain tank, y0 equals 9 feet and y20 equals 4 feet.
All right. This is, some of you noticed on one of the problems it used the term IVP,
Yes.
right?
What does that mean?
Well, okay, what would you say it says here? Y of 4 equals 20. If you,
No, it's y of 20 equals 4.
Y of 20 equals 4.
Sorry.
Yes, I did not mention IVP. I meant to. If you would have turned back a couple of pages in the section on differential equations, you would have seen IVP just means initial value problem. It just means they give you some initial values. That's all it means. So IVP is just a differential equation. Just means they give you an initial value. Well, what this is going to let us do, it's like the bank interest problem. Remember that one the other day? We put $2,000 in the bank at the beginning. That's the initial value. It allowed us to find our A value in that one problem. So what we can do with this, what does this mean? Y of 0. Remember what was Y? What was Y? The depth of the liquid. So what's the 0? The time. So at the beginning, the tank had 9 feet of liquid in it. And what's this mean then?
20 seconds.
20 minutes or whatever the time is. It's 4 feet of depth, right? At 20 minutes, there's 4 feet of depth. Okay? So all we do is we plug those in. So we put a 9 there. We put a 0 there. And we solve. So we get, well, that's just 0. So this is 9 equals 1/4 c squared. So c squared is 36. Now, we could say plus or minus 6, but because of the situation, they said that this has to be, they said because of physical properties of everything, the C minus KT has to be positive. So you couldn't put a negative here. You'd have a negative minus a positive, which would end up being negative. So we can ignore the negative 6 on that. So C is now 6. Okay, so what does that mean? Well, now my equation is this. All I'm doing, there's no calculus left in the rest of this problem until maybe the very last question. Now it's simply just working with a function and answering questions about it. Okay, I now know that C is 6. And I know that 20 minutes later, there's 4 feet in the tank. So let's plug that in. Now, I don't need, this is the part, Casey, to your questions, are going to be one like this. I do not envision one with this much solving and all that stuff. Be more like the bank interest one, simple, you plug in the number, plug in something, you got it, and there's your equation. Here we're having to plug in 2 values because we had 2 unknowns. We didn't know C, we didn't know K, right? So we're having to do this twice on this one. Normally we do it once, we plug that value in, and we got what we need. So we get 4 equals 1/4. What do we get in here? 6 minus 20k squared. What would be an easy way to do this? I sure don't want to foil that. How about we multiply the 4 over here, get 16 equals this, and then the square root. So we get 4 equals 6 minus 20k. Again, we know it can't be negative 4 because we said the C minus KT had to be positive, so we don't have to worry about that. Now we we subtract our 6, we divide by negative 20, we get 1/10. So now, when it's all said and done, our equation, we found the C and the K. So now that equation they gave us for the depth that had the C and the K in it, we now found C was 6. We now found K is 1/10. We did that with those initial conditions they gave us. They told us some things about the tank and the water dropping. So now it says, is it empty after 60 minutes?
Yeah.
So what do?
Put a 60.
Put a 60 right there. 60 times a 10 is 6. 6 minus 6 is 0. The depth is 0. Or did they ask something else? They could have asked, when will there be 20? No. When did they start out? 9. When will there be 2 feet in the tank?
2 and Y.
Then you'd put a 2 in for Y and you'd solve, right? They could just ask you some questions about the tank. Okay? And then we won't worry about the one when is the water level dropping, because that gets into the Y prime. I wouldn't ask about that. Okay? So we'll do. So back to case questions. They're going to be one like 48. The bits and pieces. You need to be able to do something like that, right? Probably not going to give you one with C's and K's and everything in it. Maybe one of those, like a K or something, but maybe not both. But the T-chart, just verify that something's a solution, right? For sure. We practiced a couple of those. And then once you have a solution, once you know something's a solution, if I give you some information then about it, you could do that. We talked about memorizing that exponential one. I don't envision, if there is a problem like bank interest or something, fine, I'll probably still give you that solution. So the stuff you'll need will be in there. Okay?
Next.
So let's talk about 49. Okay? So 49, so that's pretty much it with differential equations. We're talking about 49. We talked a little bit about maybe being able to write one, that kind of thing. That could also be more of a bonus situation too, right? We have talked a lot about that, so those kind of things could be in there. Maybe on a piece of one of these that's a little bit harder. Maybe that's something that could be in there, something like that. But the T-chart, verify something's a solution. That's the main thing. That's the main thing that I want you to be able to do with differential equations. Okay? All right, 49. 49 says, let me read this now. It says a small town charity fund aims to raise $65,000. Updated current totals are posted in the town square. According to Alfred E. Newman. Anybody know who that is? Anybody ever heard of Mad Magazine?
Yeah.
And the guy with the goofy grin and the big gap between his teeth? That's Alfred E. Newman. Anyway. What's the joke? Well, there is something called Newton's Law of Cooling, named after Isaac Newton. So that's a play. Anyway, Alfred E. Newman's law of cooling of enthusiasm, the rate at which people contribute to such a drive is proportional to the difference between the current total and the announced target amount. Okay? It says, let Y represent the current total in thousands of dollars T weeks after the drive. Okay, so the key sentence there is the rate at which people contribute. So what would that be? Y prime. That's the rate. So Y is the total dollars we have right now, and Y prime would be the dollars per, what's it say, weeks, right? Dollars per week. That's the rate at which people are giving. So now, is Y increasing or decreasing?
Decrease.
Is Y
Y.
increasing or decreasing?
Oh, yeah.
Y is the total we're raising money. So I hope it's increasing, right? Or somebody's taking off some money out of the thing. Y prime, therefore, should be positive. If Y is increasing, Y prime should be positive. Okay, I don't know if we need any of that information, but let's just understand the scenario. So Y is the total dollars given. Y prime would be the rate that people are given. Okay? So let's read that sentence. It says the rate that they contribute, Y prime, is proportional to, when I hear that word, I write down a K. Y prime means equals, proportional to, and then it says what? Proportional to the difference That means a subtraction, so I better write what right now?
Parentheses.
I better have a set of parentheses. It's proportional to the difference between the current total and the target amount. What's the current total? Y. And what's the target amount?
65,000. But it's just 65.
No, it's in thousands.
It's in thousands.
There's only 60.
You're done. That's it.
You're done.
Said, that's B. That's B. That's part B. It said write the differential equation. So it's that one sentence, the sentence where you see the word proportional, that's the sentence that tells you what to write. The rate will be in there because it's a differential equation. So the rate, y prime, is proportional to, that's where the k comes from, the difference between the amount, which they told you is y, and the target amount, which is 65,000. So that's all they wanted you to write. You don't do anything else. Yes?
The only thing I was wondering about that was your y would be less than your target amount. So would that make that negative?
Okay. So the way I wrote it, that would make y, that's a great question. Y would be less than 65,000.
Yes.
So that would make this negative. But that's okay, because what did we say y prime was? Positive. So what does k have to be in this situation? K will have to be negative, right? K is just some constant. Now, if I want to stick a negative on there, fine, then k would be positive, right? But you're right. We know y prime's got to be positive, because y is increasing. So, yeah, so what can I do? I can flip this around then, right? If I want to, I can flip this around and have this 65 minus y, and that would be correct. The difference there is then k would be positive, not negative, right?
Yeah.
Right, so k can change whether it's positive or negative, so it fits the scenario, absolutely. Because that could be a follow-up question, right? In your equation, is k positive or negative, and explain why. And that would be exactly what Jared would be hitting on there. Okay, in part B it says, does that sound reasonable? Now let's talk about this. This goes back to the part with the tank. When is it dropping on the tank problem? When is it dropping the fastest? Well, back to this. The bigger y is, this is the thing you get with a direct proportion. The bigger this side is, the bigger this is, right?
Yeah.
So the bigger y is, the bigger the rate is. So it's dropping fastest when? When it's the fullest. When it's deeper. And of course, you know that's true in those coolers, right? When it's full, man, it comes out really fast. When it gets towards the bottom, it's not coming out nearly as fast. So it makes sense that this would work, right? That this would be reasonable. And so now the same question on this next one. Does this seem reasonable? Well, when is the giving the most? When are people giving the most, or it's going up the fastest? It'd be when this is biggest. When is a difference the biggest? Well, when is a difference the biggest?
When the y is really
When there's a big difference between these two, right? There's a big difference between these two at the beginning, because y is how much is given. So at the beginning, there would be not very much given. So does it make sense that it goes up faster early? Yeah, you ever see that United Way thing up by Walmart, right, with that deal?
Yeah.
The thermometer with the red, right?
Oh, yeah.
In the beginning, people give and give and give, and then most people that have given, you know, have already given. It's harder to find more people, so that thing goes up, and then as they get towards the goal, it gets harder and harder, right? And it kind of goes up slower and slower. So it seems reasonable that at the beginning, this gap here would be widest, and that would be the biggest. That's when the rate or the rate of growth would be fastest. So that would be part A. Seems reasonable. Okay? That's it. That's everything. If you look at the assignment sheet, and that's plenty. But let's look at the assignment sheet. And I just put all right. This last line right here, I would
cookie cutter. Give me that too.
I just made up this problem right here. I just made up that problem, so I would do that as a no calculator, local max min practice. No calculator, local max min is what I would do on that one, because we said we weren't going to do global on that. Number 46 is a calculator one. That's very much like 45, right? Number 45 that we did. And we did 44 before that. Okay, so this is another one. And I would do maybe your local and your global on that one, just for practice. Local and global. I think 46 might just ask about local, and it might have done inflection points too. But you might do global, just that list of candidates. Here's a couple of, these two are a couple of verified. Those two, 26 and 27, are just a couple more T-chart ones. And like I said, if you can do those right there, there's like 4 problems. If you can do that, that's most of what the test is, right? Local max min, number line stuff, F prime, F double prime, calculator, local, global max min, verifying the differential equation. And again, don't forget those derivative rules. You're going to have some where here's a function, you just do the derivative, but you do get some practice on that in these problems also, because you have to do some derivatives in those. So you're getting that kind of practice anyway, but look through those derivative rules, especially like the log. Some of those we haven't done much, the e to the x, the log, look through those. That's it. That's everything. Now 44 and 45, those would be like number 49. I think those are just ones, I just like to throw a couple more on there to let you practice, like where you just have to, this, the rate is proportional to the blah, blah, blah. So y prime equals k times, that's a very small piece of it. Okay, or like when we were saying, is the k positive or negative, and it has to do with, we talked about the tank, the y was decreasing, so the y prime in the differential equation had to be negative. In the Alfred E. Newman problem, the amount of money was going up, so the y prime had to be positive. Okay, so that's it. That's pretty good review right there. That's everything. I mean, if you can do those things.
Is that for chapter 2?
Say that again.
That really long one.
Down at the bottom, we did some of those before our last quiz. Yeah, don't worry about that stuff at the bottom. I wouldn't mess with any of that stuff. Yeah, I wouldn't do any of those review problems at the bottom. I would just focus on what we've done. Really, we've done the same thing the last 2 or 3 days, right? It's been the same thing over and over.
And I just now got it.
And we're just now, well, it's perfect. Perfect timing.
Right?
Good thing the quiz wasn't today, right? Money on that one.
Yeah.
Hopefully, we don't get it snowed in.
Yeah, that'll be just awful.
No doubt.
I don't think it's the happiest man alive.
It's supposed to be nice today, so I think it's probably.
Pass those around. Yeah, I was gonna say, there's sure a lot of them in here.
I hope there's no
I was trying to log into
I had a question on one of them on the test, because I got taken off, I don't really know why. I think it's that one, because I went to, because I did it in my calculator, and,
Oh, on number 4?
yeah.
Like everything into what? And anything?
Right. That was what I was saying. That's what I was saying here earlier, is you needed to go more zeros to get closer. See, because you got 1653 and 1960, and it was just an estimate, and your answer has to be accurate to 3. So the right answer was 181 or 180 with rounding. That would take either one. So yeah, you're okay. Yeah, I know.
Bring this stuff out.
So, Clark,
Yes.
my test, I like to think, maybe I'll come in before school and get points back. So, it's on the back. Well, my bonus is that you might get 1 point if you have this, and I had that.
Ah,
So, I don't know. You may have seen that 5, like,
yeah.
up there.
Maybe I did. I don't think I did.
Because like I wrote it weird because that's how.
Yeah, I think so. Yeah.
And then also when I described this, I thought I would get that point just because it said the input is equal to the output. So like these aren't the same because like they don't equal, but I said it in first.
Well, you said the limit, but there is no limit. So it's not about the limit equaling the output. This only makes sense if there is a limit, like in this one. The limit is 1. And there is an output, and they're not equal. Here the reason is because the limit doesn't exist.
Okay.
So, yeah, if you said the limit as you approach C, you did, C wouldn't want to do f of 1 there either. That's what I was saying here. It's not the limit of f of 1. It's a limit of f of x as x approaches. So you put a 0. If you just said the limit as x approaches 1 from the left is 3, and the limit as x approaches 1 from the right is 1, then you put that. But I'll give you that. Yep.
Can I have a pass to come take the test with block?
And that, and where are you at then?
Music.
And you've talked to them, and that's
Yeah.
okay? And
I just need a pass.
More than okay for me.
Yeah, I just
Can you
remind you
put
I'm
both
coming in
of us?
for.
You're coming. Do you need a pass,
Well,
or you just?
we're in the same class.
Oh, okay.
So
You guys are all. You,
no,
you two are in the same.
We're in
class.
one after here for college. Yes, I'm in this. We take the test tomorrow, which is
What is it? 23. This is today, right?
So
Yes,
I spent
today.
all my time.
Thank you.
So
I just had a question. So the inflection point, so that's when we do double prime the number line, right?
Right. Right.
Okay.
And to be an inflection point, it's got to change negative to positive inflection. If you had negative, that would not be an inflection point. Because that would tell you your down stays.
Okay.
Hey, Matt. So what about what you guys were talking about earlier?
I think we're gonna take the test. Yeah, after today, Rachel and Katie. Yeah, I think we'll do it.
Katie? So we're good?
Yeah, I'll take it. Yeah.
one guy is 6 and 8.